little run through of the agenda. So today we're going to talk about RFI number 1, basic structural design, RainScreen principle, pressure equalization principles. All right. So hopefully the topics we're going to cover today. I went back and looked at yesterday's topics, and I think I did actually touch on all of them as far as just broaching the subject and introducing them. And each one of them you could keep going more and more in depth. And so for RFI number 1, let me see here. So RFIs are requests for information. And so it's just an official documentation method that the construction industry, who knows what other industries use them as well. But for the construction industry, if you have a question about the design of the building, the construction documents, that way, when we submit it, it goes to the general contractor, and the general contractor sends it to whoever, but then that gets passed around basically to every other subcontractor or whoever's working on the building. And so that's just sort of the official process of asking questions, getting the answers, documenting changes to the building, because you could have schedule impacts, cost impacts. So that's just a larger what RFIs do, right? And so there's pre-bid RFIs where if we're bidding, if multiple companies are say bidding, and we ask a question of the architect or contractor, they actually have to share that information with every other person bidding it, as opposed to just giving me the answer. They've got the responsibility of giving everybody that same information. So that's sort of a pre-bid RFI, so they can happen at any stage really during the process. And so it's really documenting questions and getting those official answers back. Because again, if they just tell us the answer, oh yeah, it's 15 feet, and we proceed with 15 feet, and we go to install, and it's 17 feet. And when you told us 15 feet, they're going, no, I didn't. Yes, I did. No. And it's all this, right? So again, it's that paper trail of official documents and things that we just want to keep and maintain. We try to do a lot of ours, just a brief overview. I'm off RFI 1, sorry. But we try to do meetings or talk to the people, talk to our customers. Again, we have relationships with our customers, and so we're working with them, trying to understand. And then what we'll do is maybe do confirming RFIs, where we send the RFI in through again to make sure everybody gets the information. But as far as getting the answer, a lot of times it's easier to have a discussion. It's just like emails. I send you an email, hey, blah, 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 blah. And you're like, dude, there's 14 questions involved in trying to understand what you're asking and understand it. So it was like an early form of emails, but it is horrible at having conversations and working to a decision, but it's great at documenting decisions. So but we'll do RFIs as well when it's just needing clarification or things like that as well. So RFI 1 for us is really us confirming the design criteria for the building. So again, we go through, like we did yesterday in our Jumpstart Package 1, where we're going through the specifications and the structural general notes, and we're getting the design criteria off of that. A lot of times, though, it doesn't have all of the information we need to be able to do our structural calculations and even sometimes our design. It may not have the exposure to help, which I need to know for the wind load, or it may not have the miles per hour, so there's some basic things that sometimes we just assume. And so again, that's as we look at, if I come back, I think this one I wanted to just go to contract. So again, this form that we fill out here, our design criteria worksheet, right? So where we're coming in and filling this out. So a lot of times these may be known or unknown. So I may not know the U factor. Sound transmittance, that's not going to be as critical for us in determining the wind load as is the wind speed, the risk category, exposure, live load deflection. And so let me see if I can find you an example of what RFI 1 looks like, actually. What I might do is this. Hmm. You have to excuse me for a second here, sorry. Should have had this all set up for me, but I didn't. No, you know what? Here's what I apologize, guys. Because that is, how do I get to that? Oh my gosh. This doesn't have sales on it. Why is that?
Why is that? Because not everybody has access to
Oh
that,
my
see?
gosh, it's terrible. So actually, you know, this probably had it. If I come back in here. Oh yeah, here we go. Let's find a newer one, because that's not going to have the new revisions that we've made to it. So again, just here's I don't even know what that means. So filling these things out, and so we label things assumed if they're not on the structural general notes or specifications if we can't find them. And then what we've done is, you know, so we're going through another thing that's important to us is the concrete strength and what the weight of the concrete, if it's normal weight or lightweight. Normal weight is stronger. Lightweight has actually a better fire protection floor to floor. So a lot of structural engineers and the contractors prefer lightweight because for whatever reason, it has better fire protection floor to floor. Something about whatever's in the concrete, but structurally, it's weaker when it comes to our embeds and things like that. So there's pluses and then there's minuses. And they usually like their pluses and don't care about our minuses.
Yeah.
So what we've done is we've created a second page behind this that then all that data that we're filling in sort of automatically fills in for us. And so this is what the minimum design criteria looks like. And so again, it's a confirmation of here's what because we're basing all of our engineering and design based on this information. So, you know, we've gone through in the past, years and years ago, before we started doing this, we would go through and do all our stuff. And then, you know, when we finally start doing calcs, it's like, oh, but the design criteria is different than what you guys thought. And it's like, oh my gosh, how silly is that? We use another different S word, stupid, but it was silly of us, right? Stupid of us, really. So this is just our first RFI so that the PM submits on every job. So again, just confirming the design criteria, the wind speed, exposure, risk category, code, what the deflections we're looking at, some seismic criteria that our structural engineers use. And so we're trying to fill in what we know and then leave blank what we don't know. So our assumptions, and then, you know, if they hope that they're filling this in and then confirming what we're also writing in there as well. And so then again, the weight of the concrete, the strength of the concrete for our embeds and anchorages, seismic drift, sort of the drift movements that the system's going to be seeing, and then the wind speed criteria. And then this is just a little chart we made over here that sometimes we can use to help fill this in automatically for us, but it doesn't show up. So the actual PDF is just this sheet over here.
And when does this RFI go out?
So once we get the job, and then it's really, so the PM is, it's a little confusion for me on whether the PM sets the meeting up with us, Jumpstart, or Jumpstart sets the meeting up with the PM, but really Jumpstart's trying to get involved with the PM to make sure the PM sends out the right information. Because to them, it's just a bunch of numbers. And it's like, oh, we don't care. They just send something in. They'd just send it in blank if they could. But the challenge there is then we get back information that's really wrong. It's like, okay, now here's the assumptions we made. Confirm this is right or not, right? As opposed to just sending it in blank. Because for them, I sent it in, sure. And it's like, well, wait, but you're not helping anyone. You're hurting us if we don't ensure that So really for Jumpstart, so yeah, the date, the timing, I'm not
No,
sure.
but it's like right after we get
Yeah.
the job, or like.
It's a week, it's a couple of weeks, but it's before.
But it
before
is
shop
truly
drawing.
the very first thing usually that gets kind of submitted. That's why we call it RFI 1.
Typically, but again, depending on the PM schedule, it may be the third one they submit, or who knows.
Yeah.
But so RFI 3, the title of RFI 3 is RFI number 1. So it's when you go to look at the portal, and so if we went over here to the portal, right, so we can go in, look at the PM dashboard. Let's look at that. So if we go to RFI, it's right there. Hey, RFI number 1. Come over here, RFI number 1 right here. So we can open it up. What it looks like. So there's what it looks like. So again, this one evidently we didn't know any of the seismic drift. We weren't sure about the live load. We were pretty sure about the seismic drift criteria and the wind load criteria. We thought we knew the strength of the strength and weight of the concrete. And so if we go back here, let's see what the response came back. See how well we did. So they've given us all the seismic criteria. Oops, they said we had the strength of the concrete wrong at the intermediate floors. It looks like the weight was right. And then live load, they came back and defined, okay, there's actually multiple different live loads. And for us, unfortunately for them, but fortunately for us, we just picked the worst. I'm not gonna have, because there's different parts and pieces. And so for us to try to combine and isolate certain parts and pieces for the live load, it's really our stack joint. We're just gonna use the same stack joint everywhere. And so we did have to create one for 5/8.
So we designed for the worst case.
Typically, yeah, in that case, yeah.
This is a good example. This is what we want.
Yep.
We want a response back, filling in all the blanks.
And
And
they've
correcting anything that we may have had.
Exactly,
Yeah, so
exactly.
it's a good example.
Sometimes, yeah, it's a great example, because sometimes
Yeah,
you go back and
sometimes
it's only halfway there, and then you
Right.
see something else. It's like, oh, come on.
Right.
All right. So that's design criteria, or RFI 1. Any questions on RFI 1?
So that's between Jumpstart and PM, right?
Yeah, so the PM submits all RFIs.
Okay.
Typically, right? I mean, if it's a sales time, the estimators will submit RFIs for pre-bid information. So yeah, so it's either the estimator or the PMs are typically the ones submitting those. Drafting can make, draft, I don't know if they do requests for, drafting doesn't really submit RFIs.
They don't
Drafting
submit
may
them.
involve as far as giving the details or the sketches or whatever to the PM, because it's usually the PM and the draftsman discussing that. Okay, here's what draftsman's going, here's what I'm looking for, I can't find it. And the PM goes, okay, well, I can't see it either, so we'll have to do an RFI or whatever to get that information for you. Okay, so the next thing was basic structural design. So since you're here, how high level or low level? Because
Well,
you could take 3 hours.
No,
or
that's what I
30
said, basic,
minutes.
just like a nice overview of, in the simplest terms, what do we design, how do we design, maybe even
Okay.
the I factor,
I value.
I values, and maybe,
Okay.
I think I've been there, just kind of just
Yeah. So
how you come up
yeah.
with the shapes and.
Okay, so we touched on that a little bit
Or,
yesterday.
okay,
No, on structural design, when we talked about package 2, right, in our pre-engineering, and I opened up sort of that pre-engineering package and showed you the results of the C-beam and the different things like that. So I'm probably going to be, you guys probably know more about engineering than I do. I'm guessing, I'm hoping.
well, not designing a curtain wall.
Well, not designing the curtain wall, yeah, but as far as engineering, and and having and knowing that the size or the configuration of a shape affects its strength.
Mhm.
So the deeper something is, or the wider, the more flanges. I mean, it's like I-beams and things, tubes, angles, just structural properties, right? So again, it's the section properties of shapes is sort of what we're looking at. Wow, that was really slow. Oh, that's not good. Oh my God.
I forget those all the time too.
I know. So we've got a little tool that we created called SecProp, SecProp, that will give you the section properties of shapes. And so when we go to our engineering, that's really what we're looking at, right? Is the I values for deflection. And so in our split vertical mullions, it's additive. So we just add up the IXX here with the IXX here. So our typical vertical mullions are 14.8.902 or something for the strength of that element. And that's the way our engineer looks at that. So when we're looking at mullion deflection floor to floor, we're using the I values of the vertical. And sort of like I mentioned, you know, as we, as the shapes get deeper, they get stronger, right? So as we, you know, differ, if we have pretty, you know, higher spans and things like that, so just by making it 2 inches longer, the male side went from 8 to 19. So again, that's probably stuff you guys already know. And if not, it's, you know, so the shape affects the properties or the strength. It really, it's, you know, just like an I-beam, it's really the thicknesses of the sort of the ends of the element. So this area here and this area back here, getting thicker or thinner, and then getting them farther apart. And you know, if I come in and try to add, you know, metal in here, which we've tried in the past, it doesn't really do us as much good in the middle of the shape. It's really at the outermost webs, and then getting them farther apart. And so for vertical mullions, you know, that's really just wind load deflection on the mullions that we're looking at. And then horizontally, we check for dead load deflection of the glass. So wind load on the horizontals, because typically horizontals, maybe you're spanning 5 feet, you know, maybe 6, 7, something like that. Maybe even 10 feet if it gets really crazy. But mullions are typically 13 feet to 16 to 18 feet because you're going floor to floor. So your mullions are almost always what you're checking. We really never check horizontals for wind load. I mean, because if it's usually what affects the horizontal the most is the dead load of the glass. And because as it gets wider, it's the narrow, because as you, it wants to bow in the middle of the glass because the weight of the glass is the corner points. And so again, this smaller number in the horizontal is what we actually are checking for dead load. So in this horizontal is the 2.337, not the 8.751. So the 8.751 is the strength in the wind load. And so, go ahead, Michael.
I just had a quick question.
Yeah.
What's the command you use to get the section properties?
Okay, it's SecProp. So SecProp. Yeah. And
So
then,
what's kind of So again, if how do you, I don't remember, do you have a tool to check the horizontal deflection? When you get to wider, I forget, do we have a tool?
Yeah, there's an engineering tool,
Okay, yeah,
that creates that, but I think Jumpstart's the only people that have.
Yeah,
that.
yeah, I just, but we do
Yeah,
check that
yeah,
when you get
exactly.
to openings
Yeah.
bigger than like
Yeah.
5-6 feet or something, right?
Yes, correct. And then just as a sort of an FYI, it's the section properties for aluminum or for steel. The actual section properties are the same. This program is written though that depending on what layer it's on, so if it's on the aluminum layer, it's the weight is going to give you the weight of aluminum. But if it's on the steel layer, which this one is, it will give you the weight of steel. So
Oh, I didn't know that.
it's got, yeah. But it's only the weight that changes. The
Oh,
section,
the I
actual-
value, we still have to
the section
multiply.
properties are still the same. Yeah. You just have to multiply by 2.9. And then just one thing that we look at on the Jumpstart side of engineering is that steel is 2.9 times stronger than aluminum. So it's so when we go to look at the reinforcing of vertical mullions, this I value here of 304, we get to multiply that by 2.9. So really what we're doing is bringing that I value up to what it would be, or to its aluminum equivalent is really what we're doing. As opposed, so we could, if the program did it the other way and said, okay, it's, understand that it's steel and it would be just this number. But if we're trying to convert it to aluminum, we would need to multiply by 2.9.
Just to clarify the term of reinforcing, so like we said, if by chance structurally the mullion doesn't calculate, we add steel members inside to reinforce it, to try to help it meet that design criteria before having to stretch it and make it visually different than maybe what the architect may have specified, right?
Right.
So stretching it is kind of like the last resort.
Yes.
If the architect specified they want a 7.5 system,
Right.
but if it doesn't work structurally, then we have to start introducing deeper systems and
Right.
other things. Yeah,
Yeah,
reinforcing
and typically the
doesn't work.
reinforcing is localized, say the corner zones where the wind loads are higher. Like we talked about that yesterday, right? The wind loads coming off the corner of the building, the little vortex it creates. Or did we or no?
Yeah, I did. When you were talking about the package 2.
Okay, good. Because I talked about it with someone else yesterday too. And I was drawing a sketch or whatever, and I go, "Was that with these guys? Was that with that other guy?" Because I can talk about it again if you need us to. Yeah, and so then we've got, like as I mentioned with the standard detail or the reinforcing, we have some standard reinforcing that we like to use and not to try to just make it easier for us. So there's a detail already drawn with the reinforcing in it. So typically we start off with a 3/4 thick by 2.5 inch steel bar, 10 foot long, centered in the span. And then if that doesn't work, our second one's 1.25 inches by 2.5. If that doesn't work, we're sort of in trouble. I mean, I could get 1.5 inches. We could get another 1/4 inch in there, which we've done before, but we really are trying to get those two to work when possible. And so then just we'll look at it again real quick too. But again, so that's what we're checking in here, right? So our deflect. So I think we looked at 1100 Broadway yesterday, but this would be an example of, in this one here, we needed that steel bar at this location for reinforcing because it's a higher floor to floor at the ground floor. And so this is how I mentioned yesterday, we indicate, not just saying, hey, here it is, and leave it to the estimator to try to find it or the draftsman. It's like we try to indicate it needs in these spots, 12 spots, and try to indicate it on here as well. And so that was CB10. And so then again, here is where we've added the reinforcing into our CV program. So doing the analysis and figuring it out. It looks like, and then in these locations here, we had to add a kicker actually. So that's what these little round dots are here. So if we look at CV1 in the corner zones and even in the typical zone. So how that looks on this is it's just another anchor symbol. So letting you know, so here's my typical ground floor anchor, my floor anchor, floor anchor, floor anchor. And then this anchor here is 4 feet below the floor. So a kicker is just another intermediate anchor just to help with the deflection because I couldn't get enough steel in the system to meet the deflection limitations. And so then that's when we had to add the kicker. That's an option we can use sometimes when we have spandrel areas, even if it's vision. They don't like it in the vision. I don't like it in the vision because you see it.
But we don't know what type of anchor is required. We just know we need an additional anchor.
At this point, yeah, at this point, yeah. So that's not designing the anchor, yeah, exactly. And then again, this sheet gives the loads that's required, at that anchor point as well. So as far as the reactions. It doesn't look like we did it here. As far as checking the horizontal deflection, typically for 5 foot or less, we're not going to have any issues with horizontal deflection from the dead load of the glass. I mean, unless it's, it would have to be really tall lights of glass. And even then, once we put the setting blocks at 8 points, at 5 feet, you're pretty stout, you're horizontal. So we don't usually check that if it's 5 feet or less. Unless it was really tall, and even then, once we check it, it's like, yeah, okay, it's fine. So that's just sort of historical knowledge, I guess. Sort of, but once we start getting wider than that, 6, 7 feet, we start seeing that deflection if it's really tall, lights of glass. So. Okay, let's see here. RainScreen. So RainScreen, the RainScreen principle is let's see if we can find some. RainScreen principle has been around for a really long time, and it's essentially where because essentially roofs are rain screens with shingles or siding where they overlap. And so again, you're screening the water away from the water line. Like in my house, if I go in my garage or go up in the attic and I look through the thing, I can see daylight. I can see little pinpricks and pinholes. So my little concrete tiles, they're not caulked together. They're not creating a water barrier where water can come through the holes. And so what the RainScreen principle is doing is it's trying to equalize the pressure from, let's say, outside of whatever the element is and the inside of the element. Because water goes where air goes, and the air moves from high pressure or from high pressure to low pressure, right? And so typically, the pressure on the outside of the building, did I say it right? Where's your low to high? But it's high. Water moves through the system, or air moves through our system, right? And so it's as the air goes, now if you put water on it as the air is moving through, that's where the water's going to go also. So like it, when I went to the Philippines, my wife's a Filipino, so we went home to see her. Out in the country, they still got just straw huts and whatever. And the pressure is equal, and it rains and no water comes in, through their thatched roofs or whatever. But it's because their buildings are so open that the air pressure inside the building is exactly the same as outside. So there's not air trying to get through all not baskets, but straw or whatever it is, the bamboo things. So the water just wants to just let gravity do the work for you. But now in America and other places, in hot climates, cold climates, we try to close the buildings up really tight to keep heat out, cold in, or cold out and heat in, right? So we almost do it to ourselves. We've created this dilemma of water because we're trying to put this hard, solid wall of air, of pressure, of pressurizing the air, because we want to keep cool in, hot out, right? Because I don't want to heat the world. I want to just heat my house, right? So as soon as I do that, I create an issue for me now with water, because now air is really trying to go back and forth due to the air pressure. So what the RainScreen principle does is what it's trying to move the shedding of the water away from the water, or that pressure differential movement. So so it's really shingles is sort of a good example. Let's see if we can find it. Oh, that's not a bad example, but let's see. Might even just go to our shop drawings and find an example. But there's one right there. Let's see. Is it gonna let me look at that? So this example here of this stone or terracotta tile right here, actually this is wood, but you can imagine that's any other material. So on this back line of the sheet of the gypboard would be an air or a water membrane. And so that's actually the water line of the building is back here, let's say. So this surface, this is air, right? This air pressure in here and this air pressure out here is the same, because these little clips are just maybe 2 inches long every so often. So air is free to circulate in and around those shapes and in and through those shapes. So I've got no pressure differential behind and in front of that. So any water that hits this, it, instead of wanting to be sucked up through that, it just wants to drain off, because there's no air pressure trying to pull the water through, air pressure moving through that. And so then the same thing can be applied to curtain walls. It can be applied to any system, right? You're really trying to, so here what you're doing is any air pressure here, it's the same. So water just wants to drain down. Incidental moisture in the air and things like that may come in here, and that's where the vapor barrier in the back prevents that from coming in. So
The type of material is for the RainScreen?
is the vapor barrier?
Yeah,
It's a type of plastic.
plastic.
It's not, so like Gore-Tex has little microscopic holes that are smaller than a water drop. So it prevents water from getting in, but it's large enough that water vapor can get out, right? So our sweat can get out. So it's permeable, it's vapor permeable, right? The vapor can move back and forth, but water can't come in. So that's why it keeps us dry, but tries to let our moisture and our sweat and our heat escape, right? So typically these are vapor barriers, so they don't have necessarily even those little tiny holes to let vapor come through or out, right? They're really trying to keep it all outside. And then this material can be anything. So like in this example, this is a wood siding, I'm guessing because it says woodcraft down here. But this could be, metal panels, it could be terracotta tile, which is a type of brick or clay that comes in a siding thing like this. It could be almost any element that you want. It could be metal, just overlapping, things like that. What we're tending to see, let's look at this one right here, maybe. And Ezzy, I don't know if I'm going too deep or too shallow. Ezzy's going, shut up, Kendall, and talk about something else. This is all good stuff, though.
No, it's good.
Let me, what I'm going to do, I'm going to go back here.
So just as you're looking, I'm just saying, so the reason to understand this though too, is understanding, most people just think the exterior thing you see on the building, that's where you're stopping the water. But as we just saw, we're allowing, so to speak, water within that in that detail we looked at, maybe 1.5 inches, it's open,
Mhm.
which is, so like I said, the water line is really that barrier. So when we are working out our details later, we'll see where's the water line, is where we need to actually stop the water from going, is where we need to seal and put the sealant. We
Yeah,
can allow water in a certain space, as Ken will show you in our details, where we allow water to go
yeah.
and air, but where we have to stop it, there is a point. So
Yeah.
just kind of ties into understanding, don't need to know every other substrate details, but it's one of those questions as we're detailing, what's the water line of that system that we're butting up to? It's not always the same. Terracotta, stone, precast, they all have different water lines. So it's just good to understand their stuff enough to know where do we need to stop the water and then understand our water lines in the curtain wall. Right.
Yeah, and so one of the current jobs, well, a lot of the jobs have this, but one is specifically is 3045 Park. And so this detail here is a vertical cut through, maybe I'll just-
A little bit.
yeah, and then I said, let me just show the elevation first. Electrical, how did I get to the electrical? So this is the plan view, and so what we're gonna be looking at is we're gonna be looking at a detail or a column. It's gonna be similar to this little vertical column cover here, and then elevation. Oh, that would have been a good sheet, yeah. Yeah, so all these, so this is all metal panel right here in this, and here's our little windows, and so these metal panels are a RainScreen panel system. So again, they're sort of that water's hitting it, shedding off, but it's not the true water line of the building. The water line of the building's behind it. And if I can find my detail again. So then looking at a plan view of that. So we've got a window.
A little bit, please. Thank you. Yeah, that's good.
I've got a window. Here, get rid of this.
It's all right. It's all
Okay.
right.
So again, I've got a window system over here. Here's my glass inside. Here's my window over here, my glass. So this is an open joint panel system. And the actual water line is this hidden line back here. This little hidden line here. So this is the water vapor barrier. And so this started in Europe actually before it got to us, and then it was really on the East Coast before it even got out to here, because it never rains in California. Well, it's raining now, but it doesn't rain. It's not like the East Coast, and it's not like Europe. And in the Bay Area especially, we don't have quite the swings in temperature that the East Coast has and even Europe. So so the Europeans even, and then now we do, this crosshatch thing here is insulation. So they'll actually come in, they put down the water line, and then they cover that with insulation. So they've sort of got a secondary element shielding water from getting back to the actual water line itself. And so normally you'd be concerned about insulation getting wet, but again, the idea is you've got to allow it to be open enough and for air to circulate through so that it's not driven rain that's hitting it, it's moisture in the air that's getting to it. And then if it because of how open they build it, it's allowed to dry. So it might get wet incidentally, but it's going to dry out. But again, it's damp, but it's not, running water, trickling water that might make its way back to the actual water line barrier, that piece of plastic, right? So what's crucial for that, for whoever's installing that product, is making sure that they leave it open to allow that air flow to go through there, right? Because a lot of times the architect will want us to go ahead and caulk it up. Oh, can you indicate? And it's like, You could, but now you're trapping water, you're making
Yeah, I
a
was gonna
fish
say,
bowl.
they show the caulking there,
Yeah.
they're not showing it as open
Right.
joint,
Yeah,
so.
and we're gonna, so just something to be aware of as you're looking at the details, if it's, if it's open joint or if it's not open joint, where it's gonna be. And then sort of, and as we mentioned here, the importance of knowing this is, if this is the true water line, that hidden line, then my window system needs to caulk to that. So right now, they don't have us caulking to that. They've got us caulking out here in the face.
Which is not the water line.
Yeah, it could be if they wanted a face sealed system, then we could caulk out there and that'd be fine. So that's where, in the proposal details, hopefully we're catching this and drawing, okay, there needs to be a little piece of flashing here and, for
We
us
need
to
a
caulk
joint
to.
up there, even though the architect didn't show it.
Right.
You see, so for us, we need to understand how we're caulking our system. We could still put the sealant where they show it,
Is a
and that would
beauty
just be
seal.
called a beauty seal. It's just for looks. That's not really waterproofing the system.
Right.
The one behind that's gonna be hidden is really the water line caulking the system.
And then the other sort of aspect is that it's typically that waterline product is not silicone compatible. And all of our sealants are silicone. And so we'll either have to come in and put a piece of metal flashing or maybe a piece of foil face tape, which essentially is, it's not duct tape, it's
It looks like duct tape,
electrician.
sort of.
Yeah, it looks like a roll of duct tape, but it's got a thin layer of aluminum foil coated to it. And so that tape will adhere to this plastic material, and then that tape will adhere to the plastic material, and then we can caulk to the aluminum foil, because we can caulk to aluminum. Silicone will adhere to aluminum. And so then I'm just going to give you a disclaimer real quick. I may be off base. 3045 may actually be a face sealed system, but so if you're thinking for a couple months, hey, Kendall said that, if you see details and you go, that's not a RainScreen, but it could be. If I just removed all those joints, then the water line would be back there. So I think it is. We've got L-word drawings. I just forget.
But it still would apply.
Yeah,
We
exactly.
still need to caulk to the water
Yes,
line.
yeah, exactly.
And this, the way it's
Right.
detailed, they're still making it clear
Sure.
that the panel is not the water
Right.
line.
But in hopefully our RainScreen discussion, or that you were hoping I was going to do.
Yeah.
Is that this, in a RainScreen system, that's the water line. And then right there, and then we would have to come in to that, add our piece of foil face tape right here. And then to that, we could caulk. And then we could add a little piece of caulking right there with some background. Little background. Man, Kendall, don't be impatient. And then do the same. I'm going, hey, this thing should just be instant, and do the same thing over here. And then, as you mentioned, if the architect wants a beauty seal. But again, one of the things to be careful of too is if it is truly a RainScreen system, that they can't have a lot of beauty seals, because again, I need that air flow to dry the insulation back out. So that's one of the areas where, when it came to the US probably the first time, and even especially with the product called EPhus, which is the initials EIFS, and so we call it EPhus, but it stands for Exterior Insulation Finishing Systems. And one of the biggest issues they were having with it wasn't that the product wasn't good, it was their installation was wrong, because they weren't installing it in such a way that the insulation could dry back out. They were putting it right on too, so the insulation would get wet, and then you'd end up getting mold years later. So they thought it was not a default, but a defect with the product. And so the industry that was doing that really hurt themselves by not going out and ensuring that people knew how to do it correctly. They just saw it was something in Europe. Oh yeah, I can do that, and anybody could do it because it's not hard. But there is a right way and a wrong way to do it. And so we don't see a lot of EPhus out here anymore. We never have really seen a lot, a little bit, but and so essentially EPhus is almost the same as plaster, but you're really just putting the plaster coat right on a piece of foam insulation or whatever, so the insulation's out there, so. Won't get too deep into that yet.
Can get into our system, we have
Yeah.
15 more minutes, so just
I
maybe.
apologize.
No, it's okay, I just wanna
Yeah.
touch on, so then show how our
Yeah.
system
Okay, yeah.
is the pressure equalized, that would be good.
So then for us, in our Windows system, Amber, okay, can everybody see that, or is that hard? Is that better or worse?
I find it worse. I like it black.
Guys?
Yeah, Amber likes the black screen.
Well, sometimes on a projector or on a thing, I actually like the white.
But your screen looks good, I think.
But on Amber's, that screen
Amber's
looks
color
fine?
looks- Yeah,
Okay. So for us, in our system, our vertical mullions, this gasket here is our air and water line. So anything, and so typically on our drawings for vertical mullions, outside is almost always to the bottom of the sheet, outside the building, and inside's on the top of the sheet. And then on our horizontal elements, outside is to the left, inside is to the right. Architects do it not quite the
Opposite.
same, almost
Yes.
opposite.
Yeah, I told them that day one, I'm like, here you go.
Architects like it the other way. So you go, how come our systems are all backset? They're not. And whether they changed or we changed, or I don't know why, but we've always drawn it this way, and I don't know why. And maybe architects have always been the other, but that's just sort of. So as we look at our vertical mullion, this line right here is this is our air and water barrier. So this gasket right here, that's where I can't have water getting through. Water comes through that, I'm in trouble. So I've got a little wiper gasket here. And so as we talk about, RainScreen and pressure equalization. So the pressure equalization was what we talked about, like with the tiles, right? The pressure behind it is the same as, so it's got enough open area and airflow. So we're trying to build the same thing into our system, is that we put these covers and things on here, but my air and water, my water and final air lines back here. So how we get the pressure in these cavities to be the same as the pressure outside is in our stack joint, is that we are open on the bottom. So did I bring that detail in? Is that our stack joint? So, and then here's that same line, that's our air and water gasket here. So that vertical gasket that we saw in the detail is coming down here, and that vertical gasket actually crosses and touches that gasket. So, but the bottom of our vertical mullion is completely open. So we're shielding a little bit with this gasket to keep wind-driven rain from getting in, but we're allowing air to come up in and inside that. So trying to keep the pressure in this area and in this area the same as the exterior area. So now I'm not pulling, I don't have air pressure differential across this gasket. So if the air is not trying to pull through there, I'm not trying to pull water through it. We do have a pressure differential here, but that's a wet seal joint, and I'm not going to have really any issues with sealant. It's really with gaskets, air trying to get through the gaskets and how tight the fit is, and then any joints in the gasket. So while I could have air trying to get through here at a sealant joint, you're not really going to have any air or moisture. There's just no possibility for that to happen.
So that just helps explain too why we only seal in the back. Also, a little bit why, it's structural as well to hold the glass. So that 371 gasket is really, again, more just aesthetic. It's more for looks and to block, like I said, direct air and water in there, but it's more
it
for
need to
looks.
prevent wind-driven rain.
Yeah, but it's not really, again,
It's not a performance.
water, not perform, thank you, so it's more for the look and install, but not so much the air. The ones in the back, 23 and 304, are doing the more water.
So pressure in here, air pressure in here, inside, the same as air pressure out here. I don't have any air flow So with no airflow, I don't have any water. So then when we do our performance test, and we're spraying water on it, 5 gallons per, I don't know how many feet per minute or whatever, it's a lot of water. So, so again, trying to keep that off of that gasket. And so I'm shingling it down, so moisture is in this area. So, vapor in the air, moisture's in the air because air is coming up from the bottom. And then as the air comes up, we actually stop it up at the head. So moisture can't come in, or air can come in this way and it can come up, but at the top, so this bottom part, just imagine that's up at the top of this other one, is the air comes up here, we do close it off up here at the top. So the air, it's not a circulating air, but it is the same. And then here at the head, we put a silicone sleeve to cover that up in the field, because the air and water can get in here as well.
So then again, so some people refer to that front area in front of the chicken head as a wet area.
Yeah.
Again, because we're saying we are allowing water to get there, that's okay, so to speak.
Yeah.
But the area behind the chicken head we call the dry area.
And
So
then-
that's where you absolutely cannot have any water go beyond the chicken head.
And this is the chicken head, in case you're
Yes,
curious. This
yeah.
little crazy looking
Did
thing.
you learn that terminology a little bit?
Yeah, why do
Okay.
they call it chicken head?
Because the way it looks.
A little rooster thingamajigger or something.
Oh, okay.
It may not really look like it. It's just the term that
It's
people
just,
use.
yeah.
We got architects saying it now, so there's no going back. It's like, once your customers saying it, once they understand it, know what it is.
Yeah, keep it.
Right, exactly. Yeah, so yeah, I'm dry back in here, so I don't account for any water being back in here. We're not doing anything. Planning for allowing for water in here. If there's water back here, we've got a leak and we need to fix it.
Yeah.
We've got something, we've got, it's a QC issue probably in the field or something. Same thing here. Oops, this is the dry area back here. Not expecting any air or water. And then all this out here is considered a wet area.
So that's why those fasteners are stainless.
Which fastener?
The one holding the pressure bar and.
Oh,
that one,
yes,
Yeah, so
right,
those are
yeah.
stainless fasteners, again, for that reason, for any incidental water that may get there, because those may get wet.
But yeah, the moisture in the air, exactly.
Yeah.
Yep.
Yeah, you
Pressure
may-
equalization system. So again, that's just getting you started,
Just a
just
basic
touching the topics.
overview, yes.
There's there's lots more. I mean, definitely if you want to Google pressure equalization or see different systems or, but I mean, so terracotta, aluminum panels, are some of the ones that we use probably the most. Typically all of our precast products are all water barrier systems. If we have stone on precast, typically, depending on what kind of stone it is, but the limestone that we use out at Stanford and SCU and a few other places, the limestone is not the water line. Limestone is very porous, and so they stick it to the concrete, but the concrete behind the stone is what's actually the water line. So we have to make sure that we're actually caulking to the concrete and not the limestone on that. So that's not really a RainScreen system, but it is, let's see, I can show you the detail real quick. Oops, right there. So yeah, so it's a stone, it's a porous stone, and when precast lays a stone down, then they pour the concrete over the top of it. There's anchors in the back of the stone, so the concrete forms around it, holds it in. So in this case, the architect didn't want to maybe see the edge, so they wanted the sealant to overlap the stone, but the true water line starts right here. at the back, at the front of the concrete, not at the stone.
So it's almost, I think my rule of thumb, we almost never caulk to any stone finish, right?
Yes, for the most part.
Most part,
Yeah, for the most
right?
part,
Like,
that's true.
So usually that's kind of like one of those gotchas, just when you see stone material, it's kind of one of those things.
Yeah.
Where's the water line? It's just one of the first questions, what are we caulking to? So they don't know what that material is, it's always safe to say the stone, we don't want to caulk to it. So you need to adjust the details like this. Again, usually architects don't show it.
Yeah, most of the stone we're seeing around here are not, they're not choosing water, they're dense enough product. It's like marble, things like that, right? It would be, there's specific
Some kind of
types.
tiles and stuff. So
Yeah.
usually,
What's
for
that
the-
job? We're doing that one job right now that Oscar did. What was that?
WNRS,
That's it right there.
that's a bunch of, I don't know what the perimeter is.
But it had some stone glazed into the windows. And so
Oh yeah,
that
that was GFRC.
was that GFRC? Oh, you're right, it was, never mind. But yeah, so again, depending on what type of stone, but most of the stones that the architect are picking in this area for the clients in this area is not a waterproof or a watertight stone, but marble is. I mean, so there's other ones as well, but it's a much denser stone that would be used. So, but we just don't see that product being used much in this area right now. Things come in and out of fashion, and so you never know, it might come back, but right now it's not in fashion. Okay, any questions, Amber or Michael?
I'm good.
Okay.
Good.
Leslie?
No.
Okay, good,
Excellent.
all right, perfect. Glad we got it recorded.
Right? Yep.
Sorry we missed yesterday.
Yeah.
And like I said, I'm always available. If you have questions, feel free to give me a holler.